Long before electric air conditioners, ancient Persians were cooling homes and storing ice by using nothing but physics, smart building, and a deep reading of climate. They did not beat desert heat with one magic machine, because the real secret was a full system built from wind, shade, water, earth, night air, and thick walls. And when people say they cooled homes to freezing, the careful version is this: they made living spaces far more comfortable and built places cold enough to preserve ice. To understand how they did it, start with the land they lived in, because this system worked so well for one powerful reason: the climate helped it work. In hot, dry parts of Iran, cities like Yazd faced fierce daytime heat, but they also had low humidity and big temperature drops after sunset. That mix matters because dry air makes evaporation stronger, and cool nights let buildings release heat instead of trapping the daytime warmth inside for days. So Persian builders did not treat heat like a random enemy, because they knew when the sun hit hardest, when the wind moved, and when the night turned cool. They built around those patterns on purpose, and that is why this story is really about engineering, not luck, not myth, and not a clever accident. The walls were a major part of the system from the very beginning, because many buildings use thick adobe, an earthen material that absorbs heat slowly. When the sun beat down outside, those thick walls delayed the heat, so the inside stayed cooler for much longer than a thin modern wall would. Then, after the sun went down and the air cooled, the building could start losing the heat it had taken in during the day. That is one reason hot, dry places are different from humid places, because a building can cool off much better at night when the air is dry. Courtyards help too, because a shaded courtyard can protect the center of a house from direct sunlight and create a calmer, cooler living zone. Basements and lower rooms also mattered, because once you move closer to the earth, temperatures become steadier and usually cooler than the burning surface above. So even before wind or water entered the picture, Persian homes already had a smart base, thick walls, shaded spaces, and cooler lower levels. Now we can move to the most famous part of the system, the Badger, which is usually called a windcatcher in English. A Badger is a tower that rises above the roof and opens toward the wind, especially in hot, dry cities where moving air can be turned into relief. In places like Yazd, windcatchers became one of the best-known parts of Persian design, and they still shape the skyline of the old city. At first glance, a Badger looks simple, almost like a tall vent, but the real design is much smarter than a hole in a wall. When wind hits the tower, pressure builds on the side facing the breeze, and that pressure pushes outside air down into the shaft. At the same time, the opposite side can have lower pressure, which helps pull stale or warmer indoor air up and back out. So the tower can bring air in and help air leave, and that means the building can breathe instead of trapping heat. Another force helps the process, and that is the simple fact that hot air rises, a motion people call stack effect or buoyancy. When warm indoor air rises, a tall tower gives it a path upward, so heat can escape instead of collecting where people are trying to live. This is why the Badger is not just a wind trap, because it uses pressure, suction, rising heat, and cross-ventilation at the same time. Some people explain it with Bernoulli's principle, and that is part of the story, because moving air can create pressure differences that help pull airflow. But Bernoulli alone is not enough to explain the whole system, because Persian cooling worked by stacking several physics effects together in one building. That is part of the genius here, because the builders did not rely on one trick, they made multiple forces help each other. The air coming through the tower was often not sent into a random room, because the next stage of the system could cool it even more. In many homes, air was directed toward a sardab, an underground chamber built below the main living areas of the house. A sardab mattered because the earth below ground stays cooler than the surface, especially when the desert sun is attacking the streets above. So when moving air traveled down into that underground space, it could lose heat simply by passing through a cooler environment. If that air also moved across cool masonry or near water, the relief became stronger, and the house could feel much better than the outdoor heat. This is where water entered the system in a very smart way, not as decoration alone, but as part of the cooling design. When air moves over water in a dry climate, some of that water evaporates, and evaporation pulls heat away from the air. Because the air in hot, arid places is usually dry, that evaporative cooling can work much better than it would in a humid place. So a Badger plus a sardab plus water was not three separate ideas, it was one chain: catch the air, move it down, cool it, then spread it. That chain is why the story feels so advanced, because the house itself was acting like a machine without needing electricity or a motor. Another key part of the system was the qanat, an underground channel that moved cool water from one place to another. Qanats brought underground water through the earth, and that water could help support cooling inside the wider architectural system. Cool water below ground is different from surface water under a burning sun because the earth protects it from direct heat. So if a windcatcher guided air toward spaces linked with cool water, the air could be made more comfortable before reaching the people inside. Again, the important point is that no one piece did everything alone, because Persian builders combined tower, chamber, water, wall, and shade into one climate system. That is why saying ancient Persians had an old air conditioner is a little too small, because they really had a full thermal strategy. And that strategy worked especially well in places like Yazd, where the weather gave them strong dry heat by day and helpful cooling by night. Yazd is one of the best cities to picture because its historic skyline is famous for windcatchers, domes, earthen buildings, and desert-adapted design. In that city, cooling was not something added after the house was built, because the architecture itself was the cooling technology from the start. One famous example stands at Dawlat Abad Garden in Yazd, where a windcatcher is often described as about 8 meters tall. It is known as one of the tallest adobe windcatchers in the world, and it shows how refined this design could become. A tower like that was not made just to look impressive, because height, openings, and internal layout all affected how the air would move. That is another reason this system deserves respect, because it was deliberate environmental engineering with clear goals and tested methods. Now we reach the coldest part of the story, the Yakhal, which is where the idea of freezing becomes real in a careful way. A yakhchal was an ancient Persian icehouse and refrigeration structure with examples often dated back at least to around 400 BCE. From the outside, a yakhchal often had a dome shape above ground, but deep storage space extended below the surface. That shape and depth mattered because the goal was not only to make ice, but also to keep it from melting for as long as possible. The walls were thick and insulating, and some examples had walls at the base around 2 meters thick, which is a serious barrier against heat. Builders often used a special mortar called saruj, made from materials such as clay, sand, lime, ash, and fibers. That mix helped create a durable and relatively water-resistant structure, which was crucial when your building was meant to guard precious ice. Think about what that means in desert conditions, because this was not a weak mud hut trying to hold cold for one afternoon. This was a carefully built cold storage structure designed to fight heat with thickness, depth, insulation, and smart seasonal timing. So where did the ice come from in a hot region? Because that sounds impossible until you look at the full system. In some places, ice could be brought from nearby mountains, which gave people a natural source during colder parts of the year. But in many places, Persian builders could also make ice locally during cold, clear desert nights when temperatures dropped enough. They used shallow pools or channels of water, and under the right winter conditions that water could freeze overnight. Clear skies and low humidity helped the ground and water lose heat fast, and that nighttime heat loss could push the water to ice. Then the ice could be cut, moved, and stored deep inside the yakhchal, where thick walls and underground space slowed melting. Because the storage area was insulated and protected from direct sun, that ice could last for months instead of disappearing in a day. That is the part of the story that makes people stare, because preserving ice for months without electricity sounds almost unreal today. But once you see the full design, it becomes less magic and more physics, insulation, timing, depth, and climate working together. This is also where the title needs a careful correction, because ordinary living rooms were not usually turned into walk-in freezers. Persian homes were not all sitting at literal freezing temperatures the way a modern refrigerator or cold room would be. What Persian engineering absolutely did achieve was very cold storage, long-lasting ice preservation, and a dramatic drop in heat stress inside homes. So the words to freezing are most honest when they point toward yakhchals and ice storage, not every room where people ate and slept. Still, even that careful version is amazing, because a society in desert conditions learned how to make and keep ice without electric refrigeration. And at the same time, it made homes, courtyards, and underground rooms far more livable through passive cooling instead of mechanical cooling. The phrase passive cooling matters because nothing here needed a compressor, power cable, or chemical refrigerant to start working. The cooling came from design, from how air moves, how heat rises, how earth buffers temperature, and how dry air boosts evaporation. That is why ancient Persian builders seem so modern, because they were solving heat by understanding systems instead of brute force. They knew a tower could catch wind, that underground rooms stay cooler, and that thick walls can delay heat like a shield. They knew water below ground could help, and they knew the night itself was a tool, not just the end of the day. In other words, they were reading climate like an engineer reads a machine, paying attention to inputs, flow, storage, and output. This is also why the system was strongest in hot arid regions and not equally powerful everywhere on Earth. If the air is humid, evaporative cooling becomes weaker because the air is already holding more moisture and cannot take much more. If dust is heavy, towers and channels can need more care, and insects or maintenance problems can make daily use harder. And many modern people want sealed interiors, filtered air, and precise temperature control, which passive systems do not always provide by themselves. So this is not a story about ancient design being perfect for every place and every lifestyle in the modern world. It is a story about a climate-specific solution that worked brilliantly where it belonged, especially in hot, dry cities like Yazd. That limit does not make the system less impressive, because good engineering is often about matching the design to the environment. In fact, modern architects still borrow many of the same ideas, even when they combine them with newer technology. They use wind towers, solar chimneys, night flushing, thermal mass, courtyards, shaded facades, and hybrid passive systems in modern projects. The tools may look newer now, but the logic is very old. Catch air, move heat, use mass, use shade, and let the climate help. That is why Persian cooling history matters so much today, because it shows comfort does not always begin with a power switch. Sometimes comfort begins with a wall thick enough to slow heat, a courtyard placed to hold shade, and a tower aimed at the wind. Sometimes it begins underground, where a sardab uses cooler earth to calm the air before it reaches the room above. Sometimes it flows quietly through a qanat, where cool underground water becomes part of a larger plan for survival and comfort. And sometimes it stands inside a yakhchal, where winter ice rests in the desert for months because the structure was built to protect cold. Put all of that together, and ancient Persian cooling stops looking like one famous old trick and starts looking like a full civilization of heat control. The Badgir caught the wind, the sardab used the earth, the qanat carried cool water, and the yakhchal stored winter like treasure. Even the walls joined the effort, because thick adobe and shaded courtyards helped hold back the worst of the daytime heat. So the real wonder is not just that these people made cool air or stored ice, but that they turned whole buildings into climate machines. They did it centuries before electric air conditioning, and they did it by understanding what air, water, sun, and earth naturally want to do. That may be the smartest part of all, because instead of fighting nature head-on, Persian builders made nature do the work. If you want to see another story where old builders solved a huge problem with smart design, watch my next video on ancient engineering that still beats modern ideas.